Hi everyone, I'm Dragos, and today I'm going to talk to you about dataplane equivalence and how we can use it in order to check network correctness. So let me start by laying the land on how network operation works these days. So basically what you have is an administrator who will get some sort of a policy from a stakeholder, and this policy is usually expressed as a natural language sentence. So what he'll try to do is essentially try to enforce this policy by writing lines of config or by programming the programmable devices in his network. So now the problem with this approach is that, well, there is a gap between the network and the configurations which the administrator has inserted in his devices and the policy that the network must obey. So now network verification comes to bridge this gap. So basically how it works is that it first will compile a dataplane model starting from the network topology and the configs, and will attempt to verify, to formally verify that this policy holds. So of course, since this policy is expressed in natural language, we cannot formally verify statements in natural language. So network verification tools require some sort of a formal policy which expresses exactly what the natural language one used to express. So if the network verification tool actually manages to show that this formal policy holds within the boundaries of the dataplane model, then you can get very strong guarantees in terms of network correctness. So now everything sounds great, but there is a problem, and the problem is that writing this sort of formal policies is hard. And usually how an administrator would go about writing a policy, he will basically specify some isolation or some reachability rules. But these rules don't capture the entire intended behavior that a network should have. So either that or showing all the behaviors, specifying all the behaviors that a network is intended to achieve is complicated because it implies writing a lot of temporal logic queries or data log queries. And this requires a lot of expert time and expertise in both networks and formal verification tools. So our goal is to essentially make it as easy as possible to specify correctness properties. And we do that by trying to find some implicit default correctness properties which must always hold in order to deem a network correct. So we claim that dataplane equivalence is an implicit way to specify policy. So let me illustrate with the following example. So what you see here is basically a cloud provider interface. So basically that's the user-facing interface on public clouds such as Azure or EC2 or OpenStack. And here the tenant may spawn VMs. He may interconnect them in intricate ways, and he may specify even security policies and so on. And what happens behind the scenes is that, well, there is a network driver which will translate from this abstract view of the network into concrete fibs, ACLs, OpenFlow rules, IB tables rules, and so on. And it will insert these rules into the devices in the provider's data center. So a very simple policy, a very simple correctness specification in this case is, well, the provider must obey to whatever the tenant had intended. But how do we actually express this kind of policy? Well, let's first observe that these two views of the network, so basically the abstract view and the implementation, are basically two data planes. So why not check that these two data planes are equivalent? Because if they are, it's clear that the provider had actually implemented correctly the tenant's intention. So I'll proceed by first defining what we mean by dataplane equivalence, and then I'll move on to showing an algorithm which solves this problem, and then I'll move on to some interesting applications where we find real-life bugs in real-life software. So first of all, a data plane, recall that it's just basically a set of interconnected boxes with a set of interconnected boxes which essentially will mangle packets and will forward them or drop them on the ground. And these boxes are not necessarily fixed function devices, such as layer 3 routers, but they may also be programmable switches, such as OpenFlow or P4 switches. So by dataplane equivalence, given 2 data planes and some input packet space, what the user does is that he will define a range of input packets that he's interested in showing equivalence for, and a set of equivalent ports in the 2 topologies. And basically, he'll try that for all packets in the input space that he's interested in, he will try to inject these packets in equivalent ports and somehow find if the outcomes of injecting this packet are in the 2 topologies are actually equivalent. And this means checking if they are output down the same port, and for some subset of interesting headers, if the values of these packets actually match. OK, so let me give you an example, and you will use this as a running example. So basically, what we have here is a client, a router, and a server. And the router is equipped with a routing table. And and how a client would send a request to the server, well, it will just follow along this path, and it will go down through to the server. So now let's assume that in this topology, we add an extra router between the existing one and the server. And what happens in this case, and the routing tables are well set up, let's assume that, and what happens is that packets will eventually reach the server. So it would appear that these 2 data planes are equivalent, but are they really equivalent? So in order to say that, let's look a bit, let's zoom into what a router actually does. Well, a router will look up an address in its routing table and will forward it to the next hop, but also it will check for expired packets, so basically when TTL is 0. And before forwarding packets, it will just decrement the TTL. So let's come back to our running example and see what happens with the packet that TTL is equal to 2. Well, it will successfully reach the server with TTL 1. But what happens in the second topology? Well, it will reach router B with TTL 1, whereby router B will essentially drop the packet on the ground. So this means that these 2 topologies are actually not equivalent, because some inputs will reach destination in the first program, but will fail to do so in the second one. So now I'm going to show you netdiff, which is our tool for checking data plane equivalence. And how it works is, well, you first of all get 2 data planes in SEFL language. SEFL language is basically the backing language of SIMNet, a symbolic network execution engine, which was presented by my colleagues at SICOM 16. And then it is also given some equivalent ports, and from each pair of equivalent ports, you will essentially be running symbolic execution on an initially unconstrained packet, and then you would check if the outcomes, if the outputs of running this symbolic execution actually match. So let's see how this works. So initially, the input space is the entire input space, all the packets which may go into this network. So what happens is that we make this packet symbolic. So basically, there are no concrete values, there are no integers there, they're just symbols. And what happens is that router A, if this condition holds, then it will drop the packet. So this will identify a subset of the input space. And this means that all packets in this subset will be dropped. And how does this carry on? So we're now working only on the blue region of our input space, and basically all the packets will eventually reach S. So now let's look at our second topology. So what we'd like to show is that for each packet in the input space, the packet is treated the same way by the network. So this naive approach would be to just enumerate all possible packets within the input space. But this is, of course, will not scale. So what we do instead is take each partition identified after running the first program and inject it into as a precondition into the first program. So let's take one by one and see what happens to these packets. So first of all, the router A will, of course, attempt to block this packet if this condition holds. And in order to check whether a condition holds, we will rely on an SMT solver. In our case, it's Z3, to ask the question, is it possible for this outcome to actually occur? So in this case, the solver will say, yes, it's possible. Now let's carry on. So what happens if we reach this place? Well, we get this condition, which is essentially the complement of the previous one. And we ask the solver, but we find that this outcome is impossible. So that's great. This means that all packets which are dropped by the first data plane are also dropped by the second one. And this is great. But now let's look at what happens when we take the inputs which will eventually reach the server in the first topology. So what happens here is that, let's see if it's possible to be dropped at router A. Solver says no. And let's continue, and let's see if it is possible for packets to get dropped at router B. Well, here the solver will say that, yes, indeed, it is possible. And furthermore, it will output an example packet which will basically violate, will go down this path. So this means that these two topologies are actually not equivalent, since some inputs will reach the server in the first example, but will get dropped in the second one. So now let's zoom out a little bit. And we've seen that in this running example that we have an outcome. So the first program outputs a successful packet, whereas the second one outputs a drop packet. And of course, these are not equivalent. But there are many more cases to consider. So first of all, what if both programs actually output a packet? And the most general case is when both programs output the same number of packets. If they output different number of packets, it falls back to the first case. Okay, so our contribution resides in solving the problem, the more general problem, where the two data planes actually output an arbitrary number of packets. And let's see how we check for one packet. How do we check if they are equivalent? Well, first of all, we need to have that they are going to be output on the same port. And second of all, we need to check whether output ports, whether all headers are actually equivalent. And we do this logically by checking if X is different from Y is not satisfiable. Okay? So in general, how we proceed is basically we are trying to find a matching between these outcomes. That is a bijection. And how we do that is, well, we will draw these edges between outcomes in the first program and outcomes in the second program. And we'll attempt to find, of course, edges are assembled in the same way as for the case where n is equal to 1. And the question is this a bijection? So in order to do this, we will compute the maximum bipartite matching, since this graph is bipartite. And this basically means the maximum number of nodes in blue which can uniquely match a node in gray. So if this number that we output is actually equal to the number of packets which went out, that means we can actually find a bijection and the results are equivalent. If they're not, that means that these results are non-equivalent, and overall, the topology will treat packets differently. OK, so now that we've seen how netdiff works, let me just show you some applications that we found really interesting in our evaluation. So the first application would be baseline testing. So what this means is that at some point, the administrator has managed to correctly configure his network in such a way that it's correct. It's tested it, and it's great. And now he'd like to change some of his configs. And the question is, are these two data planes still equivalent? Because if they are, the administrator can still be confident that his network works correctly. We ran this check for a router, for the fibs of a router in our university, in our department network. And we found that the runtime is less than 1 minute for 20,000 fib entries in a router. We also look for P4 program equivalence, whereby we essentially modify an existing P4 program. For instance, we reorder tables. So in this case, the ACL table is applied before the fib, and then the other way around. And even though these programs may seem to be equivalent, you'd be surprised to find that they're actually not. So for more details, I'll direct you to the paper. So another interesting aspect would be to check network properties, which are nice. For instance, this big switch abstraction. You'd like to abstract away your data center topology as one big switch with all end hosts connected. So we can use netdiff for this purpose also. And the last but certainly not least, we are looking for cloud provider network correctness. So I'll drill into this, since this is our most compelling use case, I'll drill into this a bit more. So what we do is that we verify Openstack Neutron. Openstack is an open source cloud software, and Neutron is its backing network driver. So how it operates, well, the user spawns VMs, he interconnects them, defines security groups, and so on, and the Neutron translates them into fibs, ACLs, OpenFlow rules, IP tables, and so on. So we must prove that these two things are actually equivalent. So how do we proceed? Well, first of all, we automatically translate each view of these data planes. We translate them into SEFL models, and then we use netdiff in order to check whether they're equivalent or not. And if they're not equivalent, most likely there is a bug, either a configuration one, either a software bug. So what we found using this approach was that we found 5 Neutron software bugs. One of them was completely novel that we reported on Neutron's bug tracker, and we found 5 configuration bugs and some tenant-level misconfigurations. So let me give you some examples on bugs that we actually found. So one of them is an isolation bug, the one that I told you we'd reported on Neutron's bug tracker, whereby this essentially violates the assumption that tenant VMs are separated. We found some unexpected interactions between different pieces of technology, and we've also found some administrator poorly configuring his topology. In this case, we found it while deploying OpenStack to our testbeds. So I'll drill in only into this unexpected interaction because I feel that this is a very compelling use case for network verification in general and for data plane equivalence in particular. So what happens here is that the tenant has spawned 2 VMs, he connected them to 2 subnets, and he interconnected them with a layer 3 router. And from his perspective, the tenant has no reasons to believe that traffic from A will not reach B. However, what we actually noticed in practice was that no TCP traffic actually reaches B. And let's explore why is that so. So what happens to packets from router A, from VM A coming into the compute node, which is basically the server which runs VM B, is, well, first of all, it will hit the integration bridge, it will pass through it, and it will reach this IP tables chain, which implements basically the security group rules for VM B. So since the packet is coming from VM A, which is in the 122.0/24 subnet, it will essentially hit this mysterious rule. And this rule will say that, well, you need to masquerade, to do network address translation for this particular packet. But due to Neutron's configurations, this packet will actually be dropped. So no traffic will ever reach B. So this means our output, so netdiff actually reports that these 2 data planes are not equivalent, and it actually shows that there are packets which are reachable from A to B in the first topology, but they are not reachable in the second one. So the origin of this mysterious rule is actually that it was inserted by libvirt, which is a tool stack for deploying VMs, and it's inserted there in order to implement the default NAT network for KVM hosts. So before I wrap up my talk, I'd like to give you some numbers on performance. So basically, on our testbed deployment, on our small-scale OpenStack deployment, we found that roughly 2,000 OpenFlow rules per data plane snapshot takes less than 5 minutes. And we've also compared fib equivalence using netdiff versus network-optimized data log. So network-optimized data log is a verification tool which basically expresses properties for networks in terms of data log queries. And we can actually express a limited version of equivalence in Node. So unfortunately, Node is less expressive than netdiff because it cannot express programmable data planes. So we can see here that the run times, so basically Node performs better than netdiff, but the larger the input, this difference drops and they become actually comparable after some point. Okay, so basically netdiff's superior expressiveness comes at relatively modest runtime costs. So just to wrap up my talk, I spoke to you about equivalence and how it is an implicit way of specifying network correctness properties. And I've shown you netdiff, which is our tool which checks equivalence between data planes using symbolic execution. And it actually manages to find some really interesting bugs in real-life software. With that, I thank you for your attention, and I'm looking forward for your questions.
Okay, so we have time for a few questions.
Hi, nice talk. Abdullah from Tufts University. So you began by motivating that we need to make policy specification easier, right? I'm just wondering whether some of the techniques that you've used can be leveraged to make this easier. So for instance, a tenant or a network operator specifies a policy. Can that be translated somehow automatically into network configurations, right? Using some of the existing machinery that you've used to verify whether two data planes are equivalent.
So I think, so basically you're asking if this data plane can be translated into actual configs?
Yeah.
Once you found that they're correct?
As in, my question is, given a policy, right, is there a way to use some of the existing techniques that you've leveraged to convert that policy into network configurations?
Yeah, so basically this is a very good direction, but at the moment we have not done anything in that respect. I guess that this would be a great idea, actually.
All right.
Yes, thank you.
So also I have a question. So how can this solution be extended to handle like stateful programs or like middle boxes in general, maybe?
Okay. Of course, handling stateful network devices is, of course, a burden, and this will basically bring symbolic execution will have this sort of path explosion. So what we do at the moment in order to model this, we've actually caught a bug which resides on, which is based on inconsistent connections in the tracker. But it only works on small inputs for the moment.
Okay. Okay, we have one more question.
Hi, Jethro from Northeastern. So very interesting work. So the question I have is that you basically deploy an OpenStack cluster and then like do the netdiff to try to differentiate them. I'm curious. So if you have, say, a large scale, real cluster in OpenStack, wouldn't that be hard to, trying to, differentiate the difference between the real, OpenStack code and then the model and stuff like that?
Yeah. So of course, the larger the inputs, the less scalable, the slower the algorithm. In order to tame exactly what you're saying, we've come up with a compositional solution, which essentially, if you have this extra information that some part of the virtual network is localized only on some specific device or in a Linux namespace, you may only want to check these bits if they are equivalent. This is what we're doing, and we've used this successfully. I mean, the runtime drops dramatically if you just take a smaller portion of the network.
Okay, thank you very much.
Okay, let's thank the speaker.